Hey everyone, this is Dr. Walker. In this video, I'm going to go over example 568, number 2, force on a semicircular conductor. In this example, we have a wire bent into a semicircle, has a radius r, forms a closed circuit, there's a current I going through, there's a uniform magnetic field going upwards, and we want to find the magnetic force acting on the wire. So the first thing to realize is that we can look at the force on the straight segment separate from the force on the curved segment. So let's do the straight segment first. Let's call that segment number 1, and then we'll do segment number 2 later. Since we're trying to find the net force, we can just add those forces on those separate segments. So let's find a force on segment number 1. We're going to use the equation just derived. It equals I integral of ds cross b along the length of the wire from A to B. The first step when using this equation is to go ahead and draw the ds on your wire. So draw a little ds, and you only need to draw one, but you do need to make sure that it's going to be consistent for the whole wire. So in this case, if we draw ds to the right, because it has to point in the same direction as the current, we know that along the whole straight wire, ds will always be a little segment pointing to the right. The next step is go ahead and find the direction of the force on this little segment. Use the right hand rule. Point your fingers in the direction of the current, which is to the right. Once you have that, and I hope you're doing it with me, you want to fold them in the direction of the magnetic field. So fold them upward. So which way is your thumb pointing? If your fingers are pointing to the right and then you fold them upward, your thumb should be pointing towards you, which is out of the page or out of the screen. So what you want to do is you want to make sure that for the whole segment that the force is going the same way, because that's the only way that you can integrate is if the force is going the same way for the whole path. All right, so the force is going out of the page, which is the k direction, the z direction, right? And it's positive z direction, positive k direction. So now we can rewrite our integral. It's going to be the integral, the cross product is going to be ds b sine of theta, but what is theta? Theta is the angle between ds and b. B is going up, so the angle is 90. Sine of 90 is 1, so we can just put dsb, don't need a sine. And let's not forget the direction. The k direction said positive z, and then the limits of integration. Well, the little ds is here. We're going to integrate along the whole length of the wire, which goes from this point here all the way up to this point. And since we know that the semicircle has a radius r, we know that this is r and this is r. We can use our given origin right here. So this point here would be negative r, and this point would be positive r. So we are integrating from negative r to positive r. We can go ahead and remove the constant b. When we integrate, ds is just going to be s from negative r to r. Don't forget the direction. And so we're going to get ib, and then we're going to get r minus a negative r, which is going to be 2r. And that's going to be the k direction. And so that is the force on the straight segment. It's going to be 2 IBR in the k direction. Now on this side, I just want to remind you that when we do have a straight segment of wire, we don't have to use this equation. We can just use the equation that we found for a straight wire, which is IL cross B. We can use this one for a straight segment of wire. If you use this one, you know that when L and B are perpendicular, which they are. Remember, L points in the direction of I. When they're perpendicular, then the cross product is just L times B. And then the length of the straight segment is just twice the radius. So 2 IBR in the K direction, we get the exact same result if we use this easier equation. So just keep that in mind. Okay, now we're ready to move on to segment 2. Let's find a force on segment 2. We're going to write our integral I ds cross B, A to B. And remember the first step, right? The first step is go ahead and draw a ds on your current wire. So it has been drawn for us already. Once you draw the ds, find the direction of the force. Use the right hand rule number 1. Point your fingers in the direction of the current of ds here. Point your fingers up and to the left. And when you do that right now, you probably have your thumb facing you. However, you have to fold in the direction of B, and B is going up. So if you have your thumb pointing towards you right now, you cannot fold your fingers upward. So you need to rotate your hand so that your fingers are still pointing up and to the left, but your thumb is now pointing away from you or into the page. That's the only way that you can fold your fingers upward. So that means your thumb, when you fold your fingers upward, your thumb is into the page. Into the page is the negative Z or negative K direction. And we did it for this segment here, but let's make sure that the force is the same direction for all segments. Otherwise, we cannot integrate as is. So let's draw a segment ds over here and point your fingers downward and to the left. You'll notice that if your thumb is into the page, you are able to fold those fingers upward. So yes, for the whole curved segment, in this particular problem, the force is into the page, so we can go ahead and integrate. They're all in the same direction. So we're going to have I ds. We're going to have B, but this time the angle between ds and B is not 90. We have an angle theta between ds and B. So you always want to identify that angle between ds and B. It was 90 over here, but it's not 90 over here. So dsB sine theta. But the force is in the negative K direction, so we do have our direction. And now, well, we know that we're going to want to integrate, and instead of integrating along this arc length here, we like to make our usual substitution, which is that ds equals r d theta. If you remember that substitution, then we'll be able to integrate along theta. So integral of r d theta b sine theta negative k. And now we have to choose our limits of integration. Well, what are we integrating theta from? If we substituted r d theta for ds, right, because ds is approximately the arc length here, and we have r d theta, then we know we have to integrate theta, where theta is going to be defined from the positive x-axis here going counterclockwise. But how do we know that this theta is the same as this one? Because sometimes it's not necessarily going to be the same angle. So in this case, these two thetas happen to be the same. And you can check that because you can draw a line going straight down here. You know that this is theta right here. You know that this is 90. And you know that the angle between this radius vector and ds is also 90 because ds is tangent to the circle. So you know that this angle over here is going to be 90 minus theta. So that tells you that this angle here must be theta. So we're lucky these thetas are the same. So we can see that we're going to integrate theta from the x-axis, which is at 0, all the way up to pi. But don't take these things for granted. You have to make sure that the angles work out. You have to make sure that the direction of the force works out so that it's all in the same direction before you can integrate. Okay, so now we're about ready. We're going to go ahead and take out the constants, I, R, B. And you know what, that negative k, I'm just going to bring that negative to the front here just so that I don't have to keep writing it in front of the k. And I'm going to integrate sine theta d theta from 0 to pi. Everything is going to be in the k direction. All right, negative IRB, and then the integral of sine is negative cosine. All right, and I keep saying that, but we're almost there. Now we have two negatives here. We're going to go ahead and cancel these out because this is multiplied here. So we can go ahead and cancel out these negatives. So we're going to have IRB, and then we're going to have cosine of pi minus cosine of 0. Cosine of pi is negative 1. Cosine of 0 is 1. So we're going to have negative 1 minus 1. Don't forget our direction. So we're going to get negative 2 IRB in the k direction for the force on segment 2, while the force on segment 1 was 2 IRB in the k direction. So what is our net force? Well, if you add those up, they're in opposite directions. They cancel each other out. The net force is 0. This leads us to two very important results. The first result is that when you have a closed current loop in a uniform magnetic field, then the force on that closed current loop in that uniform magnetic field is going to be 0. That's a great result. And then the other result, which might not be so obvious, but the other result is that if you are trying to find a force on a curved segment of wire, such as this arc here, the force on that curved segment is the same as the force on a straight segment, as long as it's carrying the same current and is pointing in the same direction. So the curved wire, the current was going from the right end to the left end. So if you replace the curved wire with a straight wire that has the current going from the right end to the left end, so the current would be going to the left. If you find a force on this straight wire, which would be opposite the force on this one, right? Since in this one the current was going to the right. The force on this straight current wire going to the left would be negative 2 IBR, right, in the k direction. So that is our second important result. The force on a curved segment is the same as the force on a straight segment that carries the same current and connects the two endpoints. Keep this in mind because it can make solving problems a lot easier if you know these two tricks.